Okay, hello, welcome. We will, in fact, be rendering today. There's a number of steps. So, first of all, let me just talk through all the steps. Okay, so obviously the previous video in the series will be very useful for sort of going in depth into the underlying concepts, how it all works. But the steps we have are, first of all, we're going to make a bunch of frame buffers and make sure that we're destroying them in the cleanup function. Then we're going to make a command pool and destroy it in the cleanup function. Then we're going to make command buffers, one command buffer for each frame and one central command buffer for the engine. And yep, there we have that. Then we're going to make the synchronization structures. And at this point, we're not going to do per frame synchronization. That'll kind of be the next video. We'll just do some very basic synchronization for the engine. So we'll make a bunch of semaphores and a fence. And then we are going to make an app class to wrap this up. So at the moment it's just an engine and it doesn't do anything. So we're going to make an app class to control everything. Then we're going to make a function to record draw commands onto a command buffer. And then we're going to make the final render function. So in keeping with that, we can go ahead and create all of the various files that we'll need. So we'll have a frame buffer header, a commands header, a synchronization header, then we'll have an app module, so basically a header and a source file. And unless I've missed everything, that's everything we'll need. Okay, so let's go to the frame buffer first. So let's go to the frame header and we'll add a little bit more here. We'll add a frame buffer, and why not, we'll add a command buffer as well. Okay, then we'll head back. And well, what will we need in our function to create a frame buffer? We're going to need a device, a render pass, and we're going to need to know how big the swap chain images are, so we'll have a swap chain extent. Okay, now I'm going to make a function which will take all of this information plus a vector of frames, and it will sort of loop through the frames and create a frame buffer for each of them. Okay, so we can see here all of the information which we need to specify in order to create a frame buffer. Hopefully this is kind of lining up with everything else that we've seen so far in the series, our general process. So now what we'll do is we will try to create a frame buffer. If that fails, it will throw a Vulkan system error. We can catch that and log that out. Okay, that's looking good. Now we can go back to our engine. Where are we? And we don't need to add, sorry, we don't need to add any other variables here because we're sort of tacking this onto our frames vector. But let's make, call this finalize setup. So this is all the sort of final little steps. Go down here and we'll call this and make the function. Now we will need access to that, so we'll include the frame buffer header. And while we're at it, let's include everything else. So we also had commands and sync. All right, so we've populated this struct and we're ready to go. We just call the make frame buffers function and we pass in the input chunk and we pass in the frames as well as our debug mode. Okay, then we can pop down here to the clean function and destroy these frame buffers. Let's run this just now just to check that it's working. And we have indeed created a frame buffer for each of these. And yeah, exited with no errors. That's looking good. Okay, so the next step is let's make a command pool. So I'll just go to the header and we'll define this. I'll make this, we'll call this command. And we're going to have a command pool. And we're also going to have a main command buffer. Okay, so let's head over to the commands header. And just as before, we'll include everything that we need. Now, a part of creating a command pool is we need to have a queue family. We need to get a queue family index. So we're also going to include the queue families header. Okay, so I'm going to make the command pool. In order to do this, we'll need a logical device as well as a physical device in order to query the queue family indices, as well as a surface. And the usual debug. Okay, so we'll get the queue family indices. and just pass this in. Physical device, surface, and debug. Okay. And now we will create a pool info. Okay, so the only thing really to mention here is this reset command buffer flag. We include this with the standard flags. Now what this means is the pool able to individually reset command buffers? Let's say we allocate, who cares? I think we're doing 4. Okay, let's say we allocate 4 command buffers, and every time we draw stuff, we grab a command buffer, reset it, and then put in some new commands to draw. Now, if we don't add this flag, then we would have to sort of reset all command buffers in the pool when any of them are reset, which it's not so good. We don't really want to do that. So that's why we're including this flag here. We'll go through the usual process. Of course, we try to create the thing and return it. And if that fails, it throws an exception, which we can catch and handle it. Okay, great. So now let's give this a shot. We'll just head over to our engine, and down below, after we make the frame buffers, we'll make the command pool. Okay, so we've now made the command pool. We can head down to the cleanup function and destroy the command pool. Let's run this and check that it does its thing. Great. Yep, it's done its thing, no errors. Good, we can continue. The next step is we need to allocate command buffers. Now remember, we have a main command buffer here for our engine, and for our frames, each frame will have its own command buffer. Okay, so we can go back to the commands header, and we can make the function for creating command buffers. Now, here for the make command pool, I didn't worry about it too much because, yeah, there are a fair number of arguments in this function, but it's manageable. But for the command buffers, I am going to make a struct to hold the arguments. Okay, with that struct created, we can then set up the command buffers creation code. The way I'm designing this is I'm going to sort of take this vector of frames, look through the frames, make a command buffer for each of them, then finally make a single command buffer and return it. This will be taken by the engine to store as its main command buffer. So, okay, fair enough. The first thing we'll do is create allocation info so that a command buffer can be allocated from the pool. Okay, This same allocation info will be used for all allocation events. Why not? Okay, so now we'll loop through all of the frames and we'll make a command buffer for each of them. Okay, with that done, we can then attempt to create and return the main command buffer. Oh, I forgot to mention. Completely forgot to mention. Okay, so obviously this function has the potential to allocate many command buffers, and so it sort of returns a vector. We're just going to select the first one. This is acceptable, because it's only going to create one. Okay, so where were we? Okay, so we've got that. Now, if we succeed, then we return that command buffer. And if we don't succeed, let's just return a null pointer. Okay, it's looking good. So we do not have to worry about destroying the command buffers because they've been allocated by the command pool. When the command pool is destroyed, that will be freeing the command buffers. Okay, so now what we can do is, oh, of course, what am I thinking? Actually create that. So we have our main command buffer here, that's fine. We'll just go over to the, oops, bit here, and we'll set this up. Okay, so we're setting that up. Let's just check that runs. And indeed, we allocate the command buffers and it runs with no errors. Okay, so now we'll create the synchronization structures. Now remember from the previous video in this series, this is one of the more sort of esoteric topics, but we're going to have 3 synchronization structures. We're going to have a fence to ensure that the run through the draw commands is sort of clean, if that makes sense, so that the draw function doesn't execute too quickly and then start again while things are still being processed in the background. And then we're going to have a semaphore which is signaled once an image has been selected, so that we're not going to render to an image until a valid image has been selected. And then we're going to have another semaphore which is only signaled once the graphics operations have been performed, so that we are only presenting an image once it has been rendered to completely. So that was just a little refresher. In order to do any of this, we're going to need to make functions to create these things. Okay, so we're just in sync.h. Okay, great. So that's our semaphore create function. really nothing too fancy there. Now we'll make a fence. The only thing to mention here is that we are including the signaled flag because when a fence is initially created, we want that fence to be good to go, because when the first frame is rendered, we need to indicate that the graphics pipeline, if you will, is ready to accept it. The first frame comes in, pops through the fence, closes the fence behind it, does its thing, then triggers the fence to open again. Anyway. Great. So that function has been created. Let's use that function. So we'll go over to Engine, and down here we'll make a bunch of synchronization objects. And now we'll create those. And finally, we can go down to the cleanup and destroy them as well. Okay, it's looking good. Let's just minimize that for now. Yeah, great. No issues. Okay, so now I'm going to do a bit of a refactor, because this is set up right now so that when we run it, it does its thing, initializes, and then exits. But I want to set it up in a loop. So I'm going to head to the app description. Okay, so the app has a pointer to an engine, which it tells to do stuff. It has a pointer to a window so that it can get input from like key presses and things. It has these variables here, which are used in frame rate calculation. And we're going to ship the window construction away from the engine into the app class. We'll also have a function to calculate frame rate, a constructor, a destructor, and this run function basically sets up the main loop. Okay, let's implement these. So as you can see here, I've also tweaked the constructor for the engine class so that it takes all of this info in. I'm just going to implement this class first, then I'll head over to the engine, tweak that, then I'll head over to the main function, tweak that. Okay, so let's go ahead. Let's grab that function and put it in. Yep, no issues there. Now we can go back and remove it from the graphics engine completely. Okay, we're almost done. This is a standard function that I use in all of my tutorial code, so I won't go through the full blow by blow. But there it is. That's one way we can calculate frame rate. And all I need to do now is destroy the app. And what we do in this case is simply delete our graphics engine. Okay, so let's update the constructor for the graphics engine. Here we are taking in width, height, window, and the debug mode. So we can go to our header and put those arguments in. Okay, and we can sort of get rid of these default values. Okay, that's looking good. Right, so I know this is a lot of back and forth, but we can go to the main and we can simplify this quite a bit. So now we just really care about the app. So we'll go and create one of those. Okay, let's run this, see what happens. Fingers crossed, no errors. Okay, it runs. What's the frame rate? This is as good as it gets, folks. About 200,000 frames per second. That's pretty good. Let's close this. And again, no errors. So now we are finally at the stage where we can write our drawing functions. Okay, so we're going to have sort of two functions. One function will record, will take a given command buffer and record a set of draw commands there, and then the other function will actually do the top level control. So let's head to our engine header, and the render function will be public, and the record command buffer will be private. Okay, let's work on the record draw commands first. Okay, so the first thing we do is begin the command buffer. Okay, and then we begin the render pass. Okay, so we have the info for creating the render pass. We're then going to define the clear color for the render pass. We're going to flash the screen with this color. Okay, so that's all the info that we need. The next step is we will begin the render pass. And then we can bind the pipeline. And draw. And remember, at this point, we're hard coding our data. We don't have any vertex buffers or anything. So we're just telling the shader, hey, just draw a number of things. So we're going to draw 3 vertices for our triangle. We're only working with one instance. As a matter of fact, we're not doing instancing. We're starting at vertex 0, and we're starting at instance 0. With that done, we can then end the render pass. Then we can end the command buffer recording. Okay, good. So there's really no way to test this without doing anything else. So let's assume that it's working okay, and we'll find out sooner or later if it's not. Now we can make the render function. So remember, basic overview of the render function. The first thing we do is we check that the path is clear for us to go. So we wait for any fences that we have to, and then we grab an image from the swap chain. Then we render to that image once the image has been successfully grabbed. Then we present that image once the image has been successfully rendered. Okay, so we want to wait for fences. Here we have it. The number of fences that we're waiting for is 1. The fence that we're waiting for is our in-flight fence. Next argument is whether we want to wait for all of the fences or just one. This is a bit weird, so let's just say true. And then we have a timeout, and timeout is in nanoseconds, so we could tell it to wait for 1 second or something. If we pass in the maximum unsigned 64-bit integer, that is a special flag to just say, just wait forever. Just wait until it happens. So we've got that. Then we'll reset that fence. So we'll sort of close the fence behind us. Okay, so we've got that. Now we will acquire an image from the swap chain. So the arguments here are the swap chain that we're going to acquire from, the timeout, which again will have no timeout, the semaphore that we're going to signal after this has been completed. And then the fence that we're going to signal, we're not going to signal any fence, so we'll just put null pointer here. And then this will sort of throw an error. We need to grab the value of that. Okay, so now we'll grab a command buffer to work with. You might be saying, hey, wait a second. Doesn't this function probably return before the image index has been properly set? And yes, you're right. This is kind of a hack because honestly, we could just use the same command buffer every time. It might work. And this definitely works anyway. So let's just leave it like that for now. Okay, now we'll record the draw commands on that command buffer. And now we will submit that command buffer, and that will actually perform the drawing. Okay, so that is actually quite involved. So again, go top to bottom. Remember, we are waiting until a valid image has been acquired for us to render to. And we also specified the stage at which we want to wait for that to occur. And as you can see here, we want to, wait just before we output color. We want to have something to output to. This should make sense. Okay, so we specified that we are waiting at this stage on this semaphore. Okay, and we specify the command buffer, which is going to be executed. And then we also specify the semaphore which will be signaled after this is all complete. Okay. Next, we will submit this. And we'll submit it on our graphics queue. So don't forget the fence. We sort of submit this draw operation, and then once that draw operation is complete, then this fence up above is opened up. So again, if this function executes really quickly, then the next execution can grab a frame before it has been presented to the screen. Okay, so the drawing has been submitted. That work is doing its thing. The next thing we want to do is present to the screen. So as before, we'll set up our present info. Okay, so that's the info that we need in order to present. Sort of makes sense. We want to wait for the semaphores which are signaled from the graphics operation. Anyway, as you can see here, this is the render finish. So we only want to present after the render has been finished. Okay, cool. So now what we can do is we can go to the present queue and present. And there's sort of one more thing that we want to do is here in the engine, we want to wait for the device to be idle before we do any deletion work, because some stuff could still be occurring here. Okay, so I guess what we can do is we can go back to our app. And in the main loop, we can tell the graphics engine to render. Okay, now, fingers crossed. Let's see. It's been a long time coming. Let's see what happens. Nice. Oh boy, that's a triangle. Gosh, I've never been happier to see a triangle. So here we have it, folks. We have created a wonderful triangle, a beautiful triangle. That's awesome. Okay. So, as I sort of hinted at, some of this stuff is a little crude still. We probably should set it up so that we can have a synchronization structure for every frame and not just sort of wait for this to do its thing. And do you know what I mean? Anyway, but we will totally tighten it up in future videos. And for now, this is a good achievement. Anyway, I hope you had fun. Hope you enjoyed this. And I will see you again soon. All right.